Okay, then we'll go to chapter 9, which should be familiar because you probably have seen some of these partial differential equation already. And we'll go through that again. And section 1, 9.1 is just an introduction. It's fairly straightforward, so you can read it yourself. But one thing I want to emphasize again, I think I talked about that before when we first encountered a discussion of partial derivative. So this is partial differential equation. Obviously, you take partial derivative, but then unfortunately the notation for partial derivative in common literature is incomplete, and so you need to be very careful in reading or keep in mind, because that becomes implicit. What I mean in incomplete is the notation doesn't give you all the information. You need to keep in mind and take into context what that means, what that partial difference. So like if you have a function f x y, right? Usually what we mean by what partial f partial x is what we say is a treat x. This should be actually be, if a more complete notation should be including what we kept constant. In this case, we are treating, when we take the partial derivative of x, we treat y constant. So there should be a notation for what constant that you keep, what other variable you keep constant. So that is important. For two variables, you just write one. I mean, that is not too cumbersome, but unfortunately, people still found it cumbersome. And then, so most likely we'll ignore that. We'll just write partial f partial x instead of an indication of what other variable are kept constant. And that, unfortunately, will lead to error, serious error. Sometimes I saw that in literature, serious error made by not keep in mind what you are keeping constant. So, and this is even more important if you do change a variable. In this case, if you change a variable, so in that case, if you choose like z is defined as whatever z depends on x and y, right? Then partial x partial f partial x is not equal to generally partial x keeping z constant. Okay, you do a change of variable, something you introduce a new variable that depends on x and y. You use that as your variable. Then, although you are still writing as partial f partial x, in both situations, that's in this case is keeping y constant. In this case, keeping z constant. But usually you don't put that. And most literature, most people write it partial derivative don't write it explicitly. And if you lose track of what is going on, you can make serious error. Is that okay? That's one thing that again remind you. I talked about that before because this is a very serious problem, very common error, a common source of error. Okay. All right. So the second section is first order. It's fairly straightforward, linear PDE. And at first, we'll use constant coefficient to make it even easier. I mean, if variable coefficient can do something like that, I think there are exercises that use variable coefficient also, but sometimes the same idea can go through with a variable coefficient. But the simplest one is two variable. First order linear one, so that's 9.1. The operator L on phi A partial phi partial x plus b partial phi partial y equals 0. So this is just a homogeneous one. Sometimes you add the inhomogeneous term that can still use this method. Okay, so but we'll establish the transformation variable first using the homogeneous, but then you can apply that to inhomogeneous solution, inhomogeneous equation also. Right, and so to solve that, basically almost all the method of solving partial differential equation is somehow convert that to ordinary differential equation or use decompose the problem to different parts and each part solve for ordinary differential equation, which you know how to solve. Supposedly you know how to solve, and that's the case. In this simple case, what we do is to do a change of variable. Right? And this first variable, your textbook called S. This S is basically just use the same coefficient, the same sign, and then just write the A. Instead of partial x, partial x, you write the A. Right. That's the first variable. And the second variable is chosen so that it's kind of like perpendicular to it in the sense that x minus ay. In the sense that you are not treating this as x and y coordinate or variable. Treat it like a unit vector. If this is a unit vector x, this is unit vector y, this is unit vector x, unit vector y, then the s dot t will be 0, right? You see that that's a s dot t become a times b minus b times a, that becomes 0. That's the idea, right? So you do that change of variable and convert that PDE to ODE. Right? That will imply what you need to do is change all this. One way to do it is change this partial derivative, so partial x. Now the x is a function of s, because you can invert that. This is linear equation. X is function of s and t, and we need to do some kind of chain rule that partial s, partial x, partial s, partial s, partial y, or not partial t, partial x, partial t, right? Then that make it partial s, partial x, a, and partial t, partial x is b, and a is b. Okay, so that's the first derivative. Again, keep in mind that this is keeping y constant. This is this s is a function of x and y. This partial derivative is keeping y constant in this context. But this partial s is keeping t constant. This partial t is keeping s constant. Okay, so keep in mind all this subtlety. Okay, and partial y. It's likewise doing exactly the same. Now partial s partial y is b, and partial t partial y is minus. Okay, these two, and you substitute it into the differential operator. A, now just substitute that one into here. You have a s plus a times partial s plus b partial t plus b, and put this here. This is operate on sine. So B, and then B is positive 5 positive S minus A positive 5 positive T. But no, what you can see is that you group the positive 5 positive S A squared plus B squared 5 positive S. And then the positive T term, you have A times B, and then minus B times A, so that's 0. That's this term. That is 0. Okay, so that becomes a ODE now, not PDE, because it depends only on one variable. Right? Solve for phi. So what is the solution? You can write down the solution. What is? Say that again. The constant, not exactly, because this, like what we talked about, this is keeping T as a constant. So what is this? Because T is a constant, so there's an arbitrary T, right? So what we mean by a constant now is anything that depends on T. Any function that depends on T, whatever we call it, phi, well, maybe just write phi as a function of T. So if phi is a function of T only, then it will satisfy this differential equation. Or where it explicitly substituted back, so the solution is phi is equal to phi x minus a. Any function that depends on this combination of variables, that would be a solution of this differential equation. Is that okay? So that kind of straightforward, right? So, and that introduces a quantity, and that is called a characteristic. Basically, this is a line. Right? This is a line that T is constant. So phi depends on T. If T is constant, then that is a solution. So it means this will be x minus ay as a constant. Right? And in this case, obviously, this is this constant coefficient, though that becomes a straight line. That and so this generally represented a line, and so in this case, this is a straight line, and that's called a characteristic. Right? The line is called a characteristic or characteristic curve. The textbook talk about it. But sometimes you're considering variable coefficient, then you can generalize that to the concept of characteristic by solving the curve. Usually you solve a curve. In this case, depends on two variables using a ODE. So in this case, a dy dx. But this one is dy dx is just simply b over a, right? It's given by a constant. In this case, a straight line. But if these are function of x, then you can integrate that and found a curve, right? And that is called a characteristic curve. And it means that that function, the solution, is constant along a characteristic. Okay, and there's some consequence of in terms of the boundary condition, whether you can set your boundary condition. Say if you have in the plane of x and y, you have a characteristic curve like that. Say, then if you choose a boundary condition, and in this case, a boundary condition would be specified a curve, and if you say you choose a boundary condition on y equals 0, then that's fine. If the characteristic is like that, then this is just one characteristic because that's involved the initial condition of this differential equation. So if there should be a family of characteristics, right? If you specify a boundary condition here, then that's okay because you just propagate whatever the value of phi at on the line y equals 0, then that value will be the same along each characteristic. And that, I mean, the boundary condition can be a function of x now, can be a function of x. But if you characteristic, all these characteristic curves just intersect your boundary curve exactly one time, then whatever the intersection value, you just propagate the value to the whole characteristic line. So that boundary condition is well defined. But if your boundary condition curve is different, so I mean, depends on however it is. So if you specify your boundary condition curve on instead of on a well-defined line that cut it just one time, you cut, if your boundary condition just cut through the characteristic 2 times, and that becomes a problem, because phi is constant here. If we set arbitrary boundary condition on a line that intersect a characteristic by more than one point, then sometimes that is in contradiction, because a characteristic that the value is the same, but then if you specify 2 different values on the same curve, then you lead to contradiction, and that you cannot find solution. Okay, and that a restriction on how you impose your boundary condition, and in particular, you don't want this characteristic be your boundary curve. So if you set the boundary condition on a characteristic, except I mean, you can set a constant that would be consistent, that you can find a solution, but then you have no value to determine the value on the other characteristic, because it's like you specify a single value, say whatever phi 0 on this curve, then that boundary condition will not be enough to solve your problem, because you don't know the value. You don't have enough information for the value on the other characteristic. So so you have solution. In this case, you have solution, but then you don't have enough information to specify your solution. Okay, so that is also not a good boundary condition. Okay, so there are some usefulness for this concept of characteristics. Okay. Is that up to here? All right, so now we'll generalize that. The next part is generalize this differential operator to slightly more general situation. So we'll just keep all this definition, and then this partial operates on psi L psi. So now you add another term, add the linear term, and that's Q, also a function x and y equals to a possible inhomogeneous term F, also a function of y, x and y, right? And now you do the same transformation, then just copy that because we did that. So the first 2 terms is still this one, a squared, b squared, y also s, right? That is fine. and then you have now Q times phi equals to F. Right? And now, do you know how to solve this one? Yes, yeah, because this is a first order linear differential equation, ODE, right? And we have talked about that. This is a very useful formula that you can always solve a first order linear ODE with the inhomogeneous term also. You just plug in that formula and find your solution. And so, but then you also need to do a change of variable in the function, all these functions. So the Q now, originally Q is a function of X and Y, but you use this transformation and convert that to a function S and T. Likewise, this is a function S and T. So when you integrate this differential equation, you're treating T as a constant or a parameter, but you integrate S as your independent variable. Just plug in the formula with because that formula involves the integration S, the integration variable. So just integrating S, not T, right? When you apply the solution. Right? And that becomes straightforward. All right, so guys, the formula is so straightforward. I don't think I need. I mean, there's example in 9.2.1, but then that so easily solved. Once you do that, once you know that you're doing it this way, then that I don't think that anything. I mean, in this example, it's just Q is just. Let's just illustrate what I mean by change of variables. So Q in this case at first is X times X plus Y, right? In that example, F is 0, which is fine, doesn't matter, right? Now, so what you do is inverse that these two transformations. So X will be whatever that is. X will be, sorry, right away. You can times A in here. I mean, times B, because you want to cancel that, right? X is multiplied by A, multiplied by B, and add the two, right? That and divided by A, B squared plus B squared, A S plus BT. Right, that's X, right? That's X. Right? And for Y is just inverse that. Y, you want to cancel this two, you want to multiply by B and multiply by A and minus subtract the two. You only also divided by the same factor. That you that is B A B S minus AT. Right. And now that becomes a function S and T that is going to be here. Now F is 0, and that would be even easier. That becomes a separable differential equations, first order one. So that is just involving a single integration, right? You don't have that becomes just a separable equation, right? So that example 9.2.1, and we have some homework problem, very simple integration. So as the first order is really not that difficult. It's okay. So up to here, this is a very simple case. Now we generalize that to slightly more general than the original one, just two variables. We add another variable. Okay, about this first. Just repeat the the exercise with adding one more term, one more variable. Let's see, partial y, partial y. Let's see. And once you do that, you know how to generalize. If you have more variable, then just keep this process going, right? And now in this case, the same change of variable for the first one is you add an extra term, just like what we did, ax plus by, and then you add c. C, this is z, sorry. Also 5 also z, right? At c times z, right? So that's your first variable. And now the second and the third one, you need the 3 variable because originally 3 variables, so you need we define 3 variable, your stu, right? And now the you do that, it's actually okay. You do that, it's actually okay. But to be general, so I mean, this is just one of many different choices that you can do, because what we want to do is just like what we did, to treat all these variables as unit vector and define 2 variables that are orthogonal to S, mainly orthogonal to S. The 2 variables can also be orthogonal to each other. You don't want it to be linear dependent because that means that you're still missing one variable. So the easiest way to make sure that they are not independent, they're not dependent, is that the dot product is 0, right? And so that's what we can do. So if you choose t just like that, then obviously s dot t is 0, right? Because still you this times that minus this b times a, that's still 0. You just don't have the z term. That is fine. And then you can choose the rest as another way to do it, right? And we can come back, but then what we do, follow your textbook, is doing is the t is called alpha sub 1x plus alpha sub 2y plus alpha sub 3 e, and u will be beta t plus beta c. Right. And again, the requirement will be s dot t 0. I mean, treating the xyz as unit vector, and then s dot u 0. And an extra condition you can impose is u term, u dot t is also 0. Yeah. It's basically like these forming just like a coordinate system, 3-dimensional coordinate system as t and u, right? And it's like a coordinate transformation. Okay, and obviously you have the 3 conditions, but then you have more parameters, and then you need, so there are many different choices that you can do, right? And we can just leave it like that at first, and then just see what will happen if we just following what we did in what we did before. So like partial phi partial x will be partial phi partial s partial phi partial x partial phi partial s partial t partial x partial phi partial t plus partial u partial u. Then it's just basically this column, right? A phi partial s plus alpha 1, alpha sub 1, partial s, partial t, beta sub 1, partial u, right? And likewise, all these other just like what we did, just use this column instead. So you have B phi positive S alpha 2 phi positive T beta 2 phi positive U phi positive Z. That's the third column. C S 3 T beta 3. Right, so that straightforward, right? So that's the same way to do it. Now the idea is substitute all these into here. So the L on phi is let's put everything in here. Now you know that finally you need to group all the terms that depends on all these three derivatives: positive phi, positive S, positive T, positive U. So group all these three so the first one is grouping positive phi, positive S. You will have A times A, so A squared, and then B times B, and then C times C, right? Yes. And then group the positive phi, positive T, and you have A alpha 1, B times alpha 2, B times alpha 3, phi positive T, and likewise for the final term you have did I get it correctly? Yeah, A times A times A. A times beta. A times beta 1, yeah, A times beta 1 plus B times beta 2 plus C times beta 3 positive phi positive U. Right, and then you require to 0. And now if you want to reduce that to differential, an ODE, then you want to kill two terms. And one way to do it, because that's a positive definite term, so everything is positive. So the way to choose all these alpha and beta, requiring both of these to be 0, you just set this to 0 and set this to 0 by your choice of alpha and beta. But this two set to 0 is just basically this two condition. So S plus S is this one, right? So this like a vector dot into here is just this one. S dot into U is just like this one, right? This two condition will set this to 0. Okay, and the final one is just to make sure S, T, and U are linearly independent. Otherwise, you just have two variables and you're missing one variable. Is okay? So that will make it a ODE, and the solution now phi is the difference that this arbitrary function will depend on the other two variables. It's still a function of two variables, T and U. Okay, but other than that, this is still a solution. So any general solution that depends on T and U, you can substitute whatever this relationship is in here, and then this in here, and that any function that depends on this kind of combination of variable that is the solution. Okay, so it's straightforward to generalize that way, and obviously if you add another variable, you can keep this going. So once you do up to 3 variables, you know how to do any number of variables. Right? It's just getting more and more complicated. Right, and now we can. So this is general choice, and just the next one you can illustrate just what we did before we write this general alpha and beta, and figure out a way to specify one simple choice. I mean, that all the choices probably depends on your question. The question can have a linear term in phi and then an inhomogeneous term. It depends on the functional form of those functions. You probably can choose this alpha beta differently, but just as an illustration, you can just say what we use the old one that we did. So use t is b x minus ay, right? That would be the t, right? And now the question is, we found all this beta to after you fix t, so this is alpha 1 minus a is alpha 2, right? Then you wanted to figure out all this beta. And one trick is to just use your cross product. So if you define u as, depends on what you want to do, s cos t, then that would be your u, right? And in that case, you can use your formula, because all these are three variables, so you just use your cross product formula. And in that case, the unit vector becomes our xyz, your xyz. And the first variable is a, b, c, right? And the second variable, s cos u, right? And then that would be t. T would be just b and minus 1. And then 0. Right. And then you can just use the cross product that minus a. So yeah, just use your cross product rule. So x will be, you have 0 here, and then minus c times a is your minus equals to a c x, right? And then y will be b c, and that will be 0. That's b times c y, and then z will be minus a squared and minus b squared. Right. And now you can check, after you do that, it's better to check whether that is actually orthogonal. So you multiply a, b, c with these three components. So what you get, you multiply a in here, a squared, and then multiply b here, b squared, and then multiply by c, and then c multiplied by here, all this cancel. So that's check, right? S times u is 0, and then whether t times u is 0, you check that. B multiplied by this one, and minus a multiplied by that one, this is 0. 0 multiplied by that, and that is also 0. You check that off, obviously it's 0. So one trick to get that using your cross product. Once you fix 2, the third one is just like your coordinate system, you just use your cross product to find the third one. Is that okay? So